All right, let's get started. So what I'm going to talk today is about code migration to Expanse. So a lot of people when they come onto the HPC systems have trouble either in knowing where the codes are, or how to compile their codes and how to get started on the machine. So hopefully with this presentation, I can give you an overview of all the different things you can do to get your code going on or your workflow going on the system. So let me go to the outline. Oops. Okay. So loosely, this is where I'm going to go. Basically, first thing is look at how you can use applications that are already available on Expanse. And you've seen a little bit of this from various talks from Mary and from Nicole, but I'll kind of dive in a little bit on the modules and the containers that are available. Then I specifically called out the Python and R based applications because this is typically where we see lots of issues where people come in with workflows that need a lot of Python or R packages, and it's not always easy to get them installed in our environment or in an HPC environment. So there are lots of options, and with both Python and R, you can look at what we have already available and also try to install using your own Miniconda instance, and also use a singularity approach. So there's lots of ways of doing it, and I'll kind of touch on every option that's available. Then the next thing is looking at how you build applications from source code. And again, here there are some interesting things when you move to an HPC machine. The libraries are usually not in the standard locations because we have our own install tree that's separate from our standard Linux location, for example. And often you'll see build instructions will just say, oh yeah, do a yum install or an apt-get install, which you can't do on an HPC system because you don't have permissions. So I'm going to show you a couple of examples of how you can use what's already installed to build your source code. And the last thing I'm going to touch on is the user built containers. I'm not going to go too much in depth there because Marty has a talk, I think, on later in the week that will talk about Singularity, and he'll go into a lot of detail there. So, but I'll just give a quick example of how that might work. So that's briefly the outline of the talk. So let's start off with basically applications that are already on Expanse. So this is the first thing you should do is if you're looking to use an application, make sure we don't already have it installed. We've seen a few users who come in and try to install packages that are already there and spend a lot of time and then figure out that, oh, they could have used the system version. So first thing to do is check to see what's there. Like we've installed and made available a huge suite of libraries and applications, as well over a couple of hundred applications and libraries on Expanse. So you should definitely check that first. This also includes like some commercial packages like QChem and Abacus and Gaussian and WASP and so on. Now, some of these have license restrictions, and you can check with us to see what the restrictions are, but they are available. And our primary approach is to make all these available using environment modules. And as Nicole was mentioning, you can use module spider to find the applications that are available that are already installed using modules. And then in addition to all this, we also have some applications like PyTorch and TensorFlow and AlphaFold that are made available using containers. And the reason we do this is because these packages typically have dependencies that won't install that easily into the standard environment. So it's much easier to do it in a container. So I'll give you examples of that. So the first thing is to see how you can use module spider. So let me pop out of this and actually pick up my terminal. So everyone can see my terminal, okay, right?
Yes.
Okay, great. Uh, so, and I'm using a training account, so there's nothing special about what I'm doing. So like, for example, now I'm looking for MATLAB and I do my module spider MATLAB, and it's going to tell you that there are two versions of MATLAB available. So now if you do module spider MATLAB 2022A, which is the newer version, you'll see it says, oh, you have to load all these modules before you can load this module. And you see that it says CPU 0.15.4, and I'll tell you why there is a CPU module. But you can see the module information is given, and it also tells you some documentation info. And if you do a module show MATLAB, it's going to tell you all the paths for where the module is located, which is this piece here. That's not so relevant, but if you scroll down a little bit, you can see the path of that's being set for MATLAB. And for every package that's has a module, we usually set the home location for that. This is not so useful for, say, MATLAB, but it might be very useful for a library like FFTW, where if you're compiling, and I'm going to talk about this later, you may need to know where exactly the library is located, and there's a variable that is set for that. So you will see that in pretty much all your modules. You can do this module show, and it'll tell you all the paths that are being set. So essentially, that's what the module is doing. It's changing your environment to include the paths and include the locations and the libraries locations into your default paths. So that is the module spider piece. Now let me go back here. And so I have snapshots just in case things didn't work. So, so we've gone through this. So one thing is, if you do module spider MATLAB 2020B, you'll see now it has got a CPU and a GPU version. And this is where I want to tell you is that we have a separate stack for the CPU nodes and GPU nodes. And the reason for this is the processor is actually different. On the CPU nodes, we have the AMD EPIC processor. So it's the ROM processor. And on the GPU nodes, we have Intel processors. So for MATLAB, it might not make a difference because the same binaries are available. But for codes that are compiled, like say we have an FFTW that's compiled, you really need to be careful which version you're using. So if you plan to run on the GPU node, you need to make sure that you first get on a GPU node and also load the modules that are corresponding to the GPU stack. Because something that's compiled for the AMD ROM processor is not going to work on the GPU node because it's a different processor, and vice versa. So if you compile on the GPU node and try to run that on the CPU node, it's going to fail. And this often happens because people load everything on the login node and try to compile, and it fails because the GPU part doesn't really work on the login node. So that's why we have those two different tracks. Now, if you do a module spider on FFTW, like I'm doing here, you will see all the combinations, right? So there is a CPU version, there's a GPU version, and then there's a bunch of versions which are dependent on the MPI that you're loading, because FFTW has an MPI component. It also has a serial version, but serial/threaded version, but most of our compiles are basically the MPI based ones. So let's let me just pop out of here and let's see how this works, right? So if I do a module reset, when you do a module reset, it will reset to the defaults. And you can see that on a CPU node, you have the CPU stock loaded by default. Now I have another window of my own where I can go to a GPU node. This won't work for everyone. It's just I'm just going to one of the nodes that I know is not in use. So if I do a module reset there, you see now it has the GPU stack loaded by default because this is a GPU node. So that's one good thing to remember, is to just do a reset. Then you will have the right stack on the right node, on every node basically. So now we did the reset. Now I'm going to do a module spider FFTW. You can see there are different versions. It also tells you that there is an AMD version too. So that's interesting. So now it's giving you all these versions. What does this mean? It means that if you want to load FFTW, you have to load one of these lines before you can load FFTW. So for example, I can do module reset and then do module load. Let's pick one. Let's pick this MPAPH one here. And now if you do module show FFTW, it's going to pick up the one that is corresponding to MVAPH. So you can see the path has MVAPH in it, and even the this FFTW library path. If you go look at the library, it's going to point to the MVAPH location for the for the MPI. Now, you can also see that in this FFTW, we are loading, we are changing a lot more things than what we had on MATLAB. And this is because you need to change the path, you need to change the dynamic library path. So if you see this location here, hopefully this is going to work. Yeah. So you can see all the dynamic libraries are located here, right? So, and you can see that there is an FFT home being set. Oh, oh no, I didn't load the FFTW yet. Okay, let me load the FFTW. And if I do echo, so now you can see it has this. And the reason this is useful is if I want to find the library location, I can just do that. So $FFTW home/lib. And this is useful if you're doing configures or if you're changing your make files to point to the right location. And as I said, if you go to like an Ubuntu or and do an apt-get install, or if you go on a CentOS machine or a Rocky Linux machine and do a yum install, these libraries will be in user lib64. So now they are located in a different place. So most configures will have to be told where they're located so that they can compile correctly. Otherwise, they'll look for it in the system paths and not find them and say that, oh, you don't have FFTW installed. That's not true. It's actually there. It's in a different place. So, and I'll show you an example of how to use this basically. So let's go back to the presentation. So we saw this. So just to summarize, you can get loading information, I mean, using module spider, and you saw all the details you could get. And once you have the right dependencies loaded, you can do a module show and it'll actually show you all the variables that it's setting. So there's a lot of information just from the module commands. The key thing to remember is the CPU and GPU stacks are completely independent. So don't mix these two. Or use the GPU stack on a CPU node or the CPU stack on a GPU node. And I've seen users do this because what they do is, oh, they do a module spider and say, oh, this library is only in the CPU stack, but I'm just going to use it. And they try to use it in the GPU and it fails. If you see something like that, the best approach is to just build the GPU version in your home directory. That'll be the quickest way to get that going. And we usually have the recipes available if someone needs to compile from source. Or you can put in a ticket like Nicole mentioned, and we can follow up. The other thing is we have a lot of examples in CM shared examples like Mary showed. So let me go there. And you will see usage information. So let's pick GROMACS. And I said GROMACS because it has both CPU and GPU. So if you go to a CPU version and look at what's loaded, so this is a example batch script. So you can just copy this over and change it to your inputs and things will work. So you can see this CPU version is set up to use the compute partition. And this is a hybrid code which uses both MPI and threads. So that's the reason you have this. And task per node is 16, which is the number of MPI tasks. And then CPUs per task is 8, which is the number of threads each of those MPI tasks will spawn. And you can see down here, I'm exporting the num threads to be matching that number. But you can see here, we are loading the CPU side of the stack. So it's module purge, module load slum, module load CPU, that gets you to the CPU. Now you could change this whole thing and remove these 3 lines and just replace it with module reset, and that will work fine too. And then we are loading GCC, OpenMPI, and GROMACS. And then you have the typical GROMACS commands below. So if you go to the GPU side of things and look at the same program, now you see I'm loading the GPU stack and then doing the open-end. So this will point to very different locations. So you have to keep that in mind. And of course, the script is different too, because now we need GPUs requested. And everything changes, and there's actually a GPU option in the GROMACS options. So basically, the first thing to do is go see if there is a module for what you're trying to run. The next thing to do is, if you find the modules, is to go to this examples directory and say, hey, do they already have a script? Because those are the standard questions we get, like, oh, how do I run this? Well, go look in the examples, you'll probably have an example. For most of the popular codes, we have examples. So let me go back to the presentation. So now that was the modules part of it. Now you might say, oh yeah, I don't see the application I want there. Before you go off and try to install it yourself, also check if we have a Singularity container for it. And this is because we've found that some of them are easy to make available via Singularity. And on expands, the containers are at in the directories CM shared apps containers Singularity. Some examples of what we do using Singularity are TensorFlow, PyTorch, AlphaFold, ParaView, and Visit. All these packages have one thing in common. They have a lot of dependencies and a lot of changes that happen frequently. So it's a lot harder for us to change the application stack that is installed on the system. So instead of that, we usually just go do a Singularity install. And in the last part of the talk, I'll show you one of the definition files to see how that works. These definition files, by the way, whatever we have in these containers, Marty's been maintaining these containers. We also have the definition files available. So if you go to the link that's in red below there in GitHub, you can find all the definition files. And these are useful for users if you want to say, you have a TensorFlow container and you say, oh, well, it doesn't have this particular Python package I need. You have 2 options if that happens. One is to get a shell in that Singularity environment and then install the Python packages under that environment and point the install to your home directory or a different directory and then use that path. That can sometimes get clunky to manage, especially if you have maybe 3 or 4 different containers you're using. It kind of gets difficult to track which one was built under which environment. So you might want to go back and rebuild the container. And then in that case, start off from Marty's definition file and then add what you need to it. And I'll show you how that is done. And Marty is going to obviously go into a lot more detail in his talk. So let me show you the container directory because there are lots of containers there. So like say you go to PyTorch, you'll see there are lots of versions there. Because often some of these packages change so much between versions that the API changes completely. And say you try to use something that works in PyTorch 1.5 in PyTorch 1.10, it's going to fail. So that's basically where these older versions will be useful, because just for compatibility, you can just use the old version that works with your particular package. Now, of course, we can't keep an infinite version level number of these old versions, but again, the definition files are in GitHub, so you can always rebuild an old version from the definition file. But the key thing to remember is that we have multiple versions, and the latest version of points to the latest thing. But if say you had an old script that suddenly stops working, first thing to do is to go check to see if the PyTorch latest recently is changed and it's pointing to a newer version, and then you can go change that out. And then we have, for example, for AlphaFold, again, we have 2 versions there. Now, we do in the examples directory, so let me choose shared examples, STSC. I think I see a question which was asking for the path, so I'm going to put the path in the help desk channel. So let me show you one of the singularity examples, right? I think if I look at TensorFlow, you'll see some singularity examples here. One thing I want to note is that the singularity module has gone to 3.9, so that needs to change. But other than that, this should work fine, I think. But you can see you're just loading the singularity module and the OpenMPI that's compatible with the version in the singularity, and I'll talk about this a little bit further down. And you're running the code via singularity, so that's how it works. So let me go back to the presentation now. So this is the example that I was showing you. Everything looks the same on the SBatch side. Just load the Singularity Pro, and then you do the execution via Singularity. Now, in this case, you'll see that we are binding a directory, couple of directories, the /expansion/scratch. This is because you're running in a container, and by default, the home directory is bound into the container, but the other directories are not. So if you don't do this bind step, it will say that the directory is missing because it doesn't find the location in the container. So that was basically applications that are already available on Expanse that we've either made available using modules or using Singularity containers. Now let's look at Python and R specifically. So starting with Python. Now there are lots of Python applications that we actually have in modules, and I have examples here of PyMATLAB, Plotlib, PyNumPy, PySciPy. But these are built with the Python that is in our application, in our module stack, right? So so you'll have to load that particular Python and then load this to get to use these. And again, if you go to the examples directory, you will see details of, and I'll probably show you one of the PySCF example to show this. Since this is in our module stack, you can use module spider and module show just like we did before to get more information. And some of these are dependent on MPI, like PySCF or PyMPI for Pi. So you will need to load the right MPIs and the Python and then load these modules. So I would say you can use this modules-based approach if everything you need for your application is in these modules. That is, like say your application needs NumPy and Pandas, and we have modules for both of them. Go ahead and use the modules version. But often what happens is users just say, oh, no, I need this other Python package that isn't in modules, and or this other thing that needs a newer version of NumPy, or your SciPy version is not doesn't have the package that I need, or whatever. Like there could be lots of reasons why what we have in the modules is not useful for you. So if you need a lot more installations, it's best to go do a Miniconda 3 or a Singularity approach. Now, if you do one of these two approaches, don't mix the modules from our stack and the Miniconda install or the container. There will definitely be conflicts and it'll fail, or the Python version will be different, or some dependency will not be there in the Miniconda instance, and then it's going to cause all kinds of problems. So if you go down the route of, oh, I need a Miniconda install, try to get everything installed in the Miniconda, whatever you need, right? So basically, go the Miniconda 3 route if the software available and the system doesn't cover your needs, like I said. Especially if this is custom installs where both Python dependencies are not there, or even sometimes non-Python stuff is missing, right? That's available in Conda and you can install through Conda. We do go the Miniconda route instead of the full Anaconda install because it's a little more lightweight in terms of space. So you should definitely start with a Miniconda instance. The next thing is install this in your home directory. Don't install Miniconda 3 into any Lustre location. I think as Andy mentioned yesterday, and I think probably Marty also mentioned, basically the Lustre location has parallel file servers behind the file system, right? So everything you do is hitting a lot more servers than your home directory, which is basically one NSF server. Now, you might think, oh, isn't that better if I hit more servers? It is better if you're writing big files and big IO blocks, because then having more servers will increase your bandwidth. But the key is with Lustre and with most of these parallel file systems is that the metadata is actually not parallelized that much. And also the number of metadata operations is higher because when you spread the file across a bunch of different targets which are on different servers, the metadata server now has to keep track of all of them, right? So there's a lot more metadata involved. And the unfortunate part about Miniconda or Conda is that they will install like 60,000 files. And when you try to load this environment, it's going to try to hit all of those files when it does the initial pass. And that causes a lot of system problems because now if you have like say 20 of these Miniconda installs in Lustre, you're going to have like continuous like 50, 20,000 file opens per second, which is really bad for Lustre and can cause system-wide problems. So that's why avoid putting Miniconda into any Lustre location. Put it in your home directory. Your home directory has 100 gigabytes, so it should cover most of your Miniconda installs. At least like I haven't seen anyone who runs out of space for Miniconda installs in the home directory. So that's the place to put it. NFS servers handle this a little bit better and also don't have impact like the Lustre situation. So that's one thing to keep in mind. The other is when you do GPU installs, make sure that the packages chosen work with the driver on the expanse GPU nodes. For example, I have the current driver version here, and that supports up to CUDA 11.6. So make sure any CUDA installs you do or CUDA-based packages you install in Python are with a version that is 11.6 or older. Like if you pick a newer version, it might fail because the driver can't support it. So you need to keep that in mind. This is especially true for TensorFlow, for example. Like it has lots of versions in Conda. You should pick the one that is compatible with the. So here I'm basically showing you an example of basically installing using Miniconda. So I do an srun to get a GPU node and get the Miniconda installer script. And this you can get from the Anaconda website. By the way, they have checksums for these scripts on the website. So when you download this, if you're doing this in your account, make sure the checksum matches before you install it. Run the script, and then it's going to ask you to review the license agreement and say yes to that. And then you can install it in your home directory, which is where it'll put it by default. Now, if you have multiple applications that you might be installing and maybe they have different dependencies even within Conda, you can use environments and to manage those. And I think Peter probably will talk about this in his talk, so I'm not going to go too much into detail there. But one thing I wanted to show you is how this looks when I do a Conda search on, say, CUDA, right? So NVIDIA has a channel where basically they have all the CUDA-based packages, including TensorFlow and PyTorch and optimized versions. So I'm doing a Conda search in the NVIDIA channel for the CUDA versions. And you can see there's version 11 onwards, but there are some that are older than what we can support. Like 11.7 will probably not work on our system because our driver is too old. So you need to keep that in mind. So, I can install a particular version, conda install -c with the channel and the CUDA and the version number. One thing to keep in mind is there are multiple channels that have CUDA installation, so you can probably find older versions elsewhere if you want. And also sometimes some packages have particular requirements. So if that happens, best thing is to create a new environment and then use the packages that you need or install the packages that you need. So here I did a conda install, and then you can see it's installing all these packages. Now, one thing to keep in mind is these packages are there in our regular environment too, but there are different versions. So this is what I mean by don't try to install versions that are basically conflicting with, like, don't try to use conflicting versions. Basically, if you're using Miniconda, just use everything in Miniconda. And one thing I noticed is it installed all the newer versions here. So I probably got something wrong when I was specifying the version. But the CUDA itself, it actually installed 11.6, so that's probably fine. Yeah. So you can actually pick and choose the versions you want when you're doing these installs. So let me move this page. Okay, so I have one separate note about MPI for Pi, and this is mainly because when you install MPI for Pi through Miniconda, you have to keep some things in mind. So the thing with MPI for Pi is this is a Python install, but it does depend on the MPI that is being used. So we have system installed versions of MPI for Pi. So if you do module spider pi-MPI for Pi, you'll see there are versions with different flavors of MPI, like mbapich2 and OpenMPI. So if you're using the modules stack for everything, you'll be okay because these were built with the MPI that's on the system. But if you are doing a mini Conda 3 install and just do a Conda based install of MPI for Pi, or sometimes you might install a package that needs MPI for Pi and Conda just pulls it in and says, oh yeah, I can install MPI for Pi. And it's going to install it. Now, the problem with that is it's going to pull in an MPI install in mini Conda of its own. And usually it's either mpich or OpenMPI. And that's okay if you're running single node. But if you go multi-node, what happens is those installs in Anaconda aren't aware of our InfiniBand network locations and the drivers for InfiniBand and so on. So what will happen is if you do a multi-node run, it's not going to use the InfiniBand network. Instead, it's going to go over probably the Ethernet network that's associated with the system side of things, which will work, but it's not going to be high performance. And also it might get you a note from us because it's like, oh, you're kind of overloading the system network instead of using the InfiniBand network, which is more appropriate for like inter-node communication. So, I mean, this is a rare case. What I've seen is generally most people using Python don't really scale up their codes going to multiple nodes or large number of nodes. But if you do end up in a situation where you need that, this will be the rare occasion where you would have to mix the MPI from external with the installation in a Miniconda. And the way we usually do that is we install everything we can in Miniconda except for the MPI parts. And we load the MPI system MPI and then build the MPI for Pi from source using the Python and Miniconda and then using the MPI externally. And that usually works okay to scale out. So it's a little complicated, but that's the best option to go forward with that. Now, the next thing I want to talk about is our applications. So again, we have quite a few applications and libraries available via modules. So if you do module spider r dash, it's going to find all the installed apps and libraries. So let me pop out of here and do module spider r dash. And I'm going to pipe it through more because this is a lot of packages. So you can see it's got lots of packages installed already, like R packages, and it's got all the combinations that you need to load, basically. Now, this is kind of a little bit of a artifact of the way we install packages is using something called SPAC. And what that does is create like all these different packages. And so sometimes it can get a little tedious if you're trying to load like, 17 different packages to get like the environment you need. But if the modules based approach works, then that is if everything you need is in already the packages that we have installed, you can use that. But just like with Python, if you really need something else, it's best to go to the Miniconda 3 or Singularity approach. Now, since we already saw the Miniconda 3 approach for the Python side, I'll show you the Singularity side here. But before I do that, same caveat here, don't mix the R apps and libraries from modules and from the ones from Miniconda 3 or in a container, because again, there's going to be conflicts and problems. Let me take a quick peek to see if there's any questions. No, I think we're good. So, so here's an example of basically using R via Singularity. Now, what I'm doing here is basically, I'm on a compute node that I got interactive access on. So again, when you do a build of a Singularity image from a Docker image, the best thing is to do it on a compute node, so where you have more space. And then I pointed the temporary directory to like /scratch $use. This should be familiar to you now, the local scratch location. loading the Singularity module and building this container from a Docker image. So often what happens with these R packages is there's already a Docker image available. So let me do this. So I'm going to move this out of the way. Oh, that's taking a while. Okay. So I'm going to do a module reset and then module load Singularity Pro and export temp directory equals /scratch $user. Oops. So that's done. And then I'm going to do Singularity. I think I have this in my history. Yeah. And by the way, I just picked one example where there was a Docker image. I mean, you might have a different Docker image that you want to build from. I just wanted to show you. So I do a Singularity build. So in this case, since we are building from a Docker image, you don't need to be root. But if you're building from a definition file, you need root access, and I'll talk about that a little bit later. And again, as I said, Marty will have a lot more about this. You can ignore that warning, and it's saying already exists because I already did a build, but it's basically you reusing those. But what you'll see is that it will grab the stuff from the Docker image and build a Singularity container from it. And this will have the R environment that's needed. So so it's creating a CIF file, which is your container image file. By the way, this for a particular application, this only needs to happen once, because once you have the CIF file, you can reuse it in subsequent runs. So you don't have to keep doing this over and over again. Oh, this is taking a while. Let me maybe background it. Because I still have the original one. So I'm going to just use that. So Singularity shell -- bind /scratch comma /expands. Oh, sorry. And then, oh, it got done. So let me just do Singularity shell -- bind /expands comma /scratch. And this image that we just created, right? So now I'm in this environment that is the Singularity image environment. So if I do, oh, good dollar. Let me see. Yeah, I can see my job and job scratch directory here, right? So that's one thing. Now, this actually already has all the paths. And if I type R into it, you can see that there was an R installation in this image with the version 3.4.3. And basically, it'll have the package that this particular application is needing. So let me quit this R instance and exit out of the Singularity shell. So basically, you just saw like an easy way to just pull the image in from Docker and just reuse it. And we've had a few R users who just had to do this because the Docker image had everything that they needed and all the paths were already set. So it was the easiest approach for them. And if you want to see how to run that using a batch script, again, it's familiar stuff on the top, asking for shared partition, just one task. And this particular code didn't really scale beyond a few threads. So we are just asking for 8 threads here. And then a memory of 16 gigabytes and the account number and 4 hours and so on. But running it is basically, now, instead of doing Singularity exec, we are doing Singularity run, because there's all in the containers, you can also have a default behavior when you run the container. So so this particular Docker image was already setting those paths up and setting it up to run the right applications. So you just do a run in this case. And there are some, this particular application needed like the directory paths to be specifically located. So that's why we are not just binding like /crush and /expands. We are binding things to a particular location. So you can see some of the input data is in this location. This was a human genome reference data set. So we just put that there. So you can basically tailor it to make the containers see the paths the way the application is expecting them and run it basically. So that's another way of running. So what we have seen is you can use our modules. You can use Miniconda 3 for both Python and R and other applications actually, or you can use Singularity. So the next thing I want to show you is how do you build everything from source, right? Sometimes users have the source code like community codes, like I'm going to give you the example of Quantum Espresso, which is a quantum chemistry code, which has the source code available and you can actually build from source. Now, usually these builds require a particular package list of dependencies. So when you build from source, you have to point to that. So let me give you an example. So this particular example is, as I said, a quantum espresso example. There is a build script if you want to take a quick look at the entire script. We actually made it into a job script. So you submit it as a job and the application gets built. So usually for anything you're building from source, the first thing you have to do is set up your modules environment to cover the dependencies that the particular code needs. So this code needed an MPI, needed a BLAS library, and needed a LEPAC library, and needed an FFTW library. So that's what we are loading. So AMD Bliss and AMD libflame are the equivalents of BLAS and LEPAC that are optimized for the AMD architecture. And the FFTW is the equivalent of FFTW3, but optimized for AMD. So that's what we are loading in this case. We are setting some compiler flags. So this is usually another thing that you need to set when you're compiling from source. Some configures will figure out what is the best flag to use, but if they have options to set the flags, you should set the flags because the automatic pickups sometimes get it wrong, especially with the AMD processors and Intel compilers. It may not detect the right CPU architecture and miss the performance basically. So in this case, we are setting basically C flags, C++ flags, and a bunch of Fortran flags. And you'll see we are setting aggressive O3 optimization, and we are saying the architecture is an AVX2 architecture. So this is what you need to give to let the configure know that, hey, this is going to be an AVX2 architecture. The other thing configurers usually look for are locations of these libraries. So remember I was saying how we set like the home locations for each library that you load using the module. So now it becomes useful because you don't have to give that huge ugly path in every setting. You can just use the relative path from the location of the library. So that's what we are doing here. Just so you know why all of these are being set, let me see if I can get my other window. So I'm basically in a source code location for Quantum Espresso. And if I do ..configure/help, it will tell you all the things you can set actually. So you can see that there are options. By the way, this is specific to this application. If you have a different application, you might have different flags and things. But you can see it's letting you set the CUDA location. It's letting you set some include paths where the HDF5 is located. There are also some flags that set locations too, like LD flags will set where the library location is. So if there is no flag for your particular library here, you can set it in the LD flag location. And similarly, CPP flags will have the include paths, and you can set it there. And you can see that this particular code also has NVCC flags, which are basically CUDA related flags on the GPU related flags on basically for a GPU compile. So so if your application has a configure, you can always do this, do a configure -- help and see what you can set, and you can set the right paths for where the locations are. And the reason we are setting paths is because our installations of these libraries are not in standard locations. They're in our SPAC locations. So now, if all of this looks a little too complicated, don't worry, send in a ticket and we can help you setting up the things. But I just wanted to point out that the locations are not standard. And so after that, I'm running the configure and setting all these things. And when you do this, the configure will have a lot of output showing you that, oh yeah, it's picking up BLAST from here, LIPAC from here, FFTW, and it's going to confirm all those things. And then you do a make to basically compile the code. So that's the codes that have configures. Some codes will just have a makefile, like a simple makefile which sets paths. And this, I think this is one such example. And in this case, I set the lib flags and include flags based on the paths on the system. Again, if this was a standard Ubuntu or CentOS installation, you wouldn't need this -L with this huge path of CM shared apps and all those things, because it would be in a standard location and pick it up. Since we don't have it in a standard location, we need to point the makefile to that. So that's where the lib flags come in and the include flags come in. And then the rest of the makefile doesn't change. One other thing to keep in mind, and I think I've said this before regarding GPU nodes regarding using modules, but it also goes for compiles. Like if you're trying to compile a code that needs to run on a GPU node, don't compile that on the login node. It's going to fail. It might compile fine, but then when you go to the GPU node and try to run it, it's going to give you a segmentation fault because it has specific requirements. And then basically it's a processor specific requirement. So there'll be some something that is AMD specific that now doesn't work on the GPU node. It's the other way too. Like if you go compile something on a GPU node, like say you compile LAMPS, which is a molecular dynamics code on the GPU node, and use the AVX512 flags because that's an Intel processor that supports it. And then you try to run that on the CPU node, which doesn't have AVX512, it's going to seg fault. So remember, if you're compiling and you think that you're going to use both the CPU and GPU nodes, you need to do 2 different compiles. The other thing I want to mention is that often, like scientific codes will require a lot of linear algebra routines and like BLAST, LIPAC, and scale-APAC. You may see that, oh, there is no LIPAC on the system for my particular compiler. That is true, but LIPAC can always be all the routines in LIPAC can be addressed from other options. For example, OpenBLAS is a good thing that covers both BLAS and LIPAC. MKL will Intel MKL libraries will cover scale-APAC. The AOCL libraries will cover scale-APAC. So this is a lot of ways of getting those. What this means is when you're compiling, like if you have a default makefile from the source code, like GitHub repo say, that may assume that, oh, there's LIPAC and user lib64. You will have to go change the makefile to point to these libraries instead, and it'll still work. So those are some standard changes you have to make. As I mentioned, libraries will be in non-standard locations. So make sure if you're using configure or cmake or makefile, all of them needs to use options that point to these other locations. And you can find the locations using module show, as I showed before. One other caveat is that Intel compilers, they work fine on AMD nodes. In fact, for some applications, the Intel compilers work faster than the AMD compiler or even the GNU compilers. So you should look at them if you're looking for performance, or sometimes some applications have specific compiler version requirements. So that's another reason you might do it. If you do use an Intel compiler, don't use the -x host flag. This is usually used by Intel based builds because the Intel compilers can detect the host. But unfortunately, that works well on the Intel based CPUs, but on the AMD based CPUs, some versions of Intel compilers will revert back to some really old architecture because they don't detect the right architecture, or they can't figure out what the architecture is because it's a non-Intel CPU, and then you'll get really poor performance. So the thing to do is to replace anything that says X host to mr arc equals core dash avx2, which basically tells the compiler it's an avx2 route, and that should be good for performance. Let me see, I have about 3 minutes, which is good. I should be able to do the last piece there. So let me see if there are any questions. No, I think we are good. So let me go back here to the user built containers. So that's the last part of it. So you might find that sometimes you will need to build your own Singularity container. And this is useful if there are lots of dependencies that you can't install in the regular Expanse environment, and we don't have a container already available. The things to keep in mind, and I'm sure Marty will go into detail and mention this more in his talk. Two things. So for MPI-based installs, make sure that the MPI in the container matches the MPI on our system, one of the MPIs on our system, because even though the container sets up the environment fine, the launch of MPI jobs is done using the external MPI. There are options to make these compatible, but it's a little tricky. So the best thing to do is to match, when you install an MPI in the container, make sure it is the same as the same version as the one that's on external. Or if you're using the InfiniBand drivers natively, again, you have to make sure that the drivers installed in the container match the drivers that are on the system. And this might be very complicated for somebody who's new. So the best thing to do is to go to Marty's definition file, start from there, because he has baseline containers that install MPI and install these drivers. So you can just start from that and then layer whatever else you need on top of it. The other thing is for GPU installs, you don't need to install the driver because the --nv flag will pull in all the info needed, but you still do need to make sure whatever packages you have installed are compatible with the driver on our system. So this goes back to the same caveat that I had with the Miniconda install. Now the builds, if you're doing from definition files, need root access. And so you can't do this on Expanse. So, but you can always build it elsewhere. So you can use your own laptop or desktop, which is what I do a lot of times. Just spin up a VM in my desktop and or my laptop and basically build as root. And as long as you have the right drivers and compatibility, you can build this anywhere and it'll work fine on Expanse. You do need to make sure that the kernel that you're using is compatible with whatever kernel is on the system. So don't go pick the latest and greatest OS, because that kernel might not be supported on our system. But other than that, you can pretty much build everywhere else. And the other nice place to do this is a cloud resource. So either in Amazon, or if you're looking on Exceed, Jetstream 2 will have options to basically spin up a VM with the right environment, and you will be root in that VM and you can go do what you need to do. So that's another way of doing it. Again, there'll be details in Marty's talk, I think. So last thing I want to show is what's in a typical definition file. Like, so this is one of Marty's examples. So you can see there are some paths being set, but mostly it's doing a lot of yum installs in this case because it's a CentOS based image. And if it was a Ubuntu based image, you could basically do a apt-get install. And then he's downloading the source and building based on this environment. But you can see there are some InfiniBand pieces being installed here. So, but I'm not going to go into detail because Marty will talk about it a lot. So going back to the summary of all the things we have looked at. So there are lots of different options to get applications working on Expanse. First thing to do is to check if it's already there. Most of the common community codes are installed. Maybe not the versions you need, but most of the time we have it installed. And if it's a code like Gaussian that is used by a lot of users, we try to keep them updated as well. The next thing to do is go look in the examples directory, make sure there isn't an example already, because that will simplify your task of creating a submit script. You can just copy over the example, change it for your inputs, and you're off, running very quickly. Then, as I mentioned, for both R and Python, there's lots of ways to do it. Look at our modules. If that doesn't work, you look at doing a mini conda install in your directory or using containers. Don't mix installation between all of these. That's the other thing to keep in mind. We saw how we can use a Docker image via Singularity. So that was a pretty quick way of getting everything in one container. Or you can build from your own definition file. So lots of different ways of getting your software on the system. One thing I didn't mention here is commercial codes. Of course, the commercial codes are cost money. So what we have installed are the ones that are quite popular. So we've kind of made the commitment on the cost side. But if there's a package that you not need that is a commercial package and doesn't work, it doesn't exist already on our system, you can check with us. Usually, depending on the budget, we can make decisions. If it's too expensive, the other option we suggest is that if you have a license, so sometimes users have a license on their home institution. And if it's a network license and you can point to it from Expanse, that is fine too, if it's allowed. Like we had a user, for example, who wanted to run OpenFOAM, not OpenFOAM, sorry, Fluent, which is a commercial CFD code. And they had an institution license and they got they checked with their vendor and they said, oh, yeah, it's okay if you run it on a different system. And we opened, basically they opened up the network connection to Expanse. All the Expanse node can talk out to the internet. So you can get to an external host if you want to do a license check, and then you can run that way. So that's a different way of doing it. With that, I think I'll stop. I think I'm a few minutes over already. So